Okay, thank you, Jason, for that introduction. Like we said, my name is Brad Llewellyn, and my job is to help individuals and organizations kind of unravel what data science is and how they can use it to get from wherever they are to where they really want to be. So this presentation is going to focus around Azure Machine Learning Studio. That's distinct from Azure Machine Learning Workbench, which is a newly released piece of local software. All of this is going to be in the web GUI. And what we're going to do is we're going to walk through a particular use case of how we would solve a problem in the real world, and not just how would we build one model that may or may not be good enough. How would we build hundreds of models so that we can build a production-ready model that everybody can agree this is good enough. And to do that, we're going to show 4 different tips that we use to make sure that our models are great. A little bit of information about me. My name is Brad Llewellyn. I'm a data science consultant for an organization called Llewellyn. We'll talk about them in a second. I have the plethora of certifications over on the right side. I've been an analytics consultant for about 5 years. I've been with Llewellyn for almost 2 now. If you want to reach out to me after this presentation, you can find me on Twitter at BreakingBI. You can find me on LinkedIn, as well as my blog at breaking-bi.blogspot.com. After this presentation, there will be some code, and I will post it up on my blog as a special post. So if you want any of the code we used today, you can see it, because there will be a little bit of that. But small plug about Llewellyn. Llewellyn is a full-stack IT consultancy, meaning we do everything from software development, app dev, to web dev, project management, infrastructure, security, and we have a data team, which is what I'm a part of. So we handle the customer's entire technology lifecycle. Everything they need, we can handle. Want to give a really big plug to the PASS Cloud Virtual Group, which is, as Jason mentioned, that's who this presentation is being done for. I'm a huge advocate of the PASS organization, and would definitely emphasize that everybody go out and join as many virtual groups or local groups as you're comfortable with. They're great ways to learn. I'll also say it's a great way to volunteer and give back to the community, because there are thousands, hundreds of thousands of data professionals out there looking for help, and PASS is really good at helping them. So it's a great way to give back to your community. So today's scenario, I'll give everybody about 30 seconds to read through this so that we know what we're trying to accomplish. Okay, so our goal here is to build a predictive model that predicts a user's income. For those of you that have seen the first presentation I gave about a month ago, this is an extension of that. So that presentation, we talked about very basic, what is Azure Machine Learning and how do we even use it? Now we're going to take that basic knowledge, which you don't have to have seen the presentation, but if you have, it may be helpful. We're going to take that basic scenario and we're going to flesh it out and do it in a professional manner. How would we, if we were professionals, approach this problem? And that's what we're going to see throughout. So in order to do that, here are the 4 tips. First, we're going to talk about letting the data decide, and we'll talk about exactly what that means, because if you leave with one thing only from this presentation, that needs to be it. That is the most important thing to really elevate everyone here to being a true data professional, is letting the data do the work for you. We're also going to talk about tune model hyperparameters, which is a module in Azure Machine Learning. We're going to talk about ways to postpone feature engineering and why that's helpful, as well as ways to extend Azure Machine Learning Studio using SQL, R, and Python. So first and most importantly, letting the data decide. Here's a list of as many data science algorithms as I could pull off Wikipedia. This isn't even remotely all of the data science algorithms in the world. In fact, this is just regression. There's probably 20 times this many algorithms in the world. We could certainly read through this entire list. I'll tell you, I don't know what 3/4 of these even are. And any data professional that tells you that they're an expert in all of data science is lying. In fact, this list is so robust and so long, I bet most of you haven't even noticed there's a few Pokemon thrown in here. So when we talk about being data science professionals, we cannot be the true mathematical experts that know everything. We can't look at a data set and go, oh, I need to use a generalized linear model for this. I need to use robust regression, because we don't know everything. So one of the ways we can get around this is by letting the data tell us which algorithm is best, not us making that distinction for it. So what does a traditional data scientist do? Traditional data scientist is a lot of math. I've seen proposals and work done by what I would consider traditional data scientists. And a lot of it is based on these 7 assumptions about the data. Here's the type of model we'd recommend because of these, and they go through a whole bunch of axioms, and it really turns into just being assumptions and guesses based on previous experience. And seeing as how when we walk into a project, we don't know what that data is. We might know some things about it, we might know where it comes from or what fields are there, but we don't know all of the patterns in the data. So we couldn't possibly know what model's best. So we're trying to break this paradigm here. We're trying to say we don't know what model's best. Let's let the data tell us. So what would your life look like if you used Azure Machine Learning in this way? This is what I want my life to look like. I want to be able to take my wife and kids and go to the water park every day, because we're letting the data decide for us, and we're letting Azure Machine Learning do all the hard work instead of us having to sit around all day tweaking parameters and whatnot. So since we're talking about what a traditional data scientist is and what we're trying to become right now, what's a data scientist in the future going to look like? You know, these algorithms are getting stronger and stronger, so what's obviously the next step? Well, I hate to tell you is it's obviously extinction. But our goal is to do as much as we can before the Terminators come back and wipe us all out. Jokes aside, the whole point we're trying to make here is the cloud is so powerful, so much more powerful than we are, that we should allow it to do as much of the work as possible. We should allow it to churn through tens, hundreds, thousands, tens of thousands of models if we want, and tell us what's best, not the other way around. So what's the first way we can do that? Azure Machine Learning has a module called Tune Model Hyperparameters. And we'll see this in action here in a minute. Before we do that, let's think about, why does predictive modeling take so much time? Why doesn't a data scientist come in and solve your problem in a day? First, as we saw before, there are so many different types of models, and they all have slightly different tweaks. Some of them are similar, some of them are completely different. So churning through that takes time. It takes manual time if we're having to make assumptions and do the work ourselves. It takes computational time if we're having the computer do it for us. Regardless, it takes time. Next, each of these models has parameters, most of which are numeric, meaning they have thousands of different values you could put in them. You could be 0.1, 0.2, 0.3. I've seen professional data scientists take time to manually input parameters into models. And as you can imagine, that goes one at a time. And that's not efficient when we have hundreds of model types and thousands of parameters. So we need a way around that. And third, outside of the models themselves, there are dozens of different ways to clean your data. And we'll talk more specifically about that later. Once we combine all of this together, it just turns into work. It is a lot of work. So that's why traditional predictive modeling takes so much time. Our goal is to take as much of this as possible and put it onto Azure so that Azure does all of it for us and we can go to the water park with our kids. So back to the what if. What if the computer did all of this for us? Let's take a look. Hop out to Azure Machine Learning Studio. I've got my experiments out here. Quick reminder of our goal here. Our goal here is to predict income based on demographic data. Of course, that starts with a data set. So let's take a look at our data set here in the middle. We'll visualize this. This is a set of demographic data about 32,561 people up here. And we have 15 data points. We have age, work class, financial weight, education, marital status, occupation, the list goes on. At the very end here, we have a column called income. and that takes two values. It takes less than or equal to 50K and greater than 50K. This is what we're trying to predict. Given the other 14 columns, when this new user logs on to the website, can we predict their income? That's what we're going to do today. So, first step to building a predictive model is we have to deal with something called a testing and a training split. We can have an entire presentation on optimal ways to do this. But in general, training a model is like taking an empty math formula and then applying your data to it. So these models start out as empty equations, and then you take your data and you smash them together and you get a trained model, a model that makes predictions. In order to determine how well that model makes predictions, we need to do what's called testing or evaluation. And imagine that I was training you to identify Picasso paintings. I would show you some paintings that are Picasso. I'd show you some paintings that aren't Picasso. Would it be fair for me to show you a painting you've already seen and ask you whether it's Picasso or not? Not really, because you should already know. Humans don't have perfect memories, but the computer does. So the computer should already know. So it's not a fair test. The better test is for me to show you a Picasso painting you haven't seen and ask you whether or not it's Picasso. And that's what the testing and training split's designed to handle. In some cases, this can be quite complicated. I just worked a project where we actually had to go through 4 different iterations of how to split our data because the real-world scenario was so complex that replicating it became a challenge. Here, it's actually really easy. We can just split our data randomly. We can just put part of it in one direction, part of it in the other. We're doing this with a module called split data, and over on the right side, we can see we have a 70% split. That's just personal preference for me. I've seen people go 50-50. I've seen 60-40. In general, it doesn't matter much. Go with whatever fits your fancy. Basically, this means that 70% of our data is going to be used to train the model, and then 30% is going to be used to test it. Just to verify, we can open up the left side of this, which should have the 70%. And it has about 23,000 rows, which is about 70% of 35,000 rows. So we're good. Moving on, we'll go to our next experiment. Now that we have the bare bones, let's look at tune model hyperparameters. We have our input here and our split just as we had before, but we've added 2 new modules. First module is our untrained model. So in order to use tune model hyperparameters, we have to have a model. This model is the 2-class boosted decision tree. I just chose this one now. It generally turns out to be the best in practice. So if you had to choose one, this is the one I would generally choose. However, as we're going to see at the end of this presentation, you don't have to choose. Azure Machine Learning can choose for you. This boosted decision tree has 4 parameters that we have to set. We have the maximum number of leaves per tree, the maximum number of samples per leaf, the learning rate, and then the number of trees. And based on how we tweak these, our accuracy or precision or recall or whatever metric we use could change dramatically. So choosing these becomes a major part of the equation, and that's what we saw in why modeling takes so long. So if we look down at tune model hyperparameters, what tune model hyperparameters does is we give it a number of runs. So we say, I want you to run 5 times. I want you to build 5 models. And for those 5 models, I want you to predict a column. In our case, we want to predict income. And we want to give you a metric to decide what's best. So it'll create those 5 models. It'll calculate all the different metrics, and we just need to give it a way to sort it. What metric we choose down here doesn't actually matter. It's going to run all 5 anyway. All it affects is how it sorts the results. So when we're choosing a metric for classification, we have to keep something in mind. So let's hop back up to our income. When we look at this income, we see something. We see that the less than or equal to 50K category is substantially larger than the greater than 50K category. Its frequency is actually 76%, which means that 3 out of every 4 users that log onto the website have an income of less than or equal to 50K. This is what's known as an imbalanced class. And as the classes get more and more imbalanced, going to 80%, 80-20 or 90-10, or heck, I've seen 99.9 to 0.1 before. As it gets more and more imbalanced, The traditional metrics of accuracy and AUC fall apart mathematically. Just thinking about it here, in our case, if we wanted to build a model with 76% accuracy, we could build that model just by always predicting less than or equal to 50K. We'd be right 76% of the time. So you can see once that gets to 80 or 90 or 95 or 99, our models get really, really accurate just by always predicting the most common category. There are ways around that. There are other metrics like precision and recall and F1 that combat that. In our case, 75-25 isn't that imbalanced, so we're just going to use accuracy and AUC. However, there are use cases in which we've used precision recall, and in practice, I commonly use precision and recall. So as we go on here, we see I chose accuracy. We could have easily chose AUC. They're generally pretty close as far as their ordering. So let's see what the results of this are. What it's done here is it's taken our 5 models, and it's created all of them, and it has calculated all of our metrics for all of these models. So we can see the 5 different models here, all their parameters, and we can see the accuracies for all of those. The worst model had an accuracy of just under 85%, and the best model had an accuracy of just over 86%. This data set's pretty clean. In fact, I would be suspicious that it might even be fake, but it's not our data set. In practice, I've seen this make dramatic differences. I've seen this make the difference between a model simply not working at all to being exceptional. So the parameters we choose can make a tremendous difference. And that's what two model hyperparameters lets us do, is it lets us churn through lots of different models. In this case, I chose 5. In production, I'll generally choose 20, 30, 50, 100 even for some of the faster models. It all depends how large your data is and how much time you're willing to invest in. So here we can see that our best model so far, best in quotes, has 6 leaves, 47 number of records per leaf, a learning rate of just under 0.15, and 233 trees. And it gives us an accuracy of just over 86%. So that's the first tip. Use tune model hyperparameters to let Azure Machine Learning pick your parameters for you. So let's move on. Postponing the feature engineering. This is an interesting one, and it's pretty hit or miss as to whether the people I talk to about it appreciate it or think it's blasphemy. So we'll leave it up to you to decide which side of that fence you're on. But first, let's talk about what is feature engineering. Feature engineering is the attempt to improve your model accuracy using the data you already have. So we have this set of data, and it has 14 different columns in it, 15 if you count the column we're trying to predict. Feature engineering wants to create new fields. For instance, we oftentimes see people create new fields out of, like there's a financial weight column in there, which is skewed, so people would use things like square root and log and things like that. There are some cases in which people would use sines and cosines and whatnot. So depending on your situation, you can create new fields out of just existing fields like that. The most common way we see it used is aggregating existing fields. In this example, that's not that useful. However, when you have time-based data, for instance, looking at sales by month, very often we see, I want this month's sales, and I want the sales for the last 3 months and the sales for the last 6 months, and those would all be different columns, all created off of the same column. And finally, you can combine multiple fields into a single field. This is often called interactions, and we'll actually see us do this here later in a few minutes. So now that we know what feature engineering is, let's talk about the traditional data science cycle. Remember, we're trying to break this traditional cycle. We're trying to not have to do the math all day and spend all day behind the computer. We want to go to the water park, and we're gonna talk about how to do that. So in here, we start with data collection. We move on to data cleansing, meaning taking that data we've collected and making sure that it's ready to be used in a model. Oftentimes, making sure that we don't have any fake data in our data, any data that's missing, any data that's just outright wrong. We try to alleviate a lot of that. Then we move on to feature engineering, which is what we just talked about. Once we have our data cleaned and our new features engineered, that's when people finally start creating their first model. They've done a whole bunch of work before they've ever created a model. They have no idea how good their model is going to be while they're doing their cleansing and feature engineering. And that's always struck me as a bit odd. And once they create their model, then they do their evaluation. And then if their model's good enough, it goes to production. If it's not good enough yet, then it goes back through the cycle again. Right? You keep going and going until you decide to quit, until you get to a point that's appropriate, until you want to change your problem. There's a lot of different ways out of the cycle. We want to focus on these two phases right here, the cleansing and the feature engineering. I propose those are optional. You don't actually have to do them. People do them because a model that has features that have been well engineered will obviously outperform a model that doesn't. Otherwise, your feature engineering isn't done very well if it doesn't actually improve your model. But what if your original model was good enough? What if you could have built a model without doing all of that additional work, without spending days or weeks or months doing additional work? What if your first model was already good enough? Can it already go to production? Isn't that good enough for a phase 1, and then you can save the feature engineering and the cleansing for a phase 2? Perhaps. I've seen that happen. Another thing I've seen happen is, what happens if your original model is so bad that you couldn't possibly fix it with data cleansing or feature engineering? That would be good to know as well, because then you're not wasting days, weeks, or months cleaning up data for a problem that you ultimately can't solve anyway. In fact, I just had a project where both of those happened. One of the problems we were solving was pretty much solved right off the bat. Just the data we were able to put together gave us such a high accuracy that the client was willing to say, I'm willing to test this in production. Well, not test in production, but test in alongside production for the next couple of months. And the other problem we were working on turned out to be so bad that there was no way to fix it with feature engineering. So we had to go back and reevaluate our problem statement and try to redesign it so that we can solve it in a different way. So let's talk about how we would do this in practice. Hop back out to the studio. Go back to our next experiment. So this is pretty much the same experiment we've seen before. We've got our input coming in, we've got the split data and the tune model hyperparameters, but we've added a little bit here. At the end here, we want to use something called permutation feature importance. However, as a bit of a quirk of Azure Machine Learning, the models themselves will allow you to put in string data, but permutation feature importance doesn't like it. So instead, we decided to do what's called indicator values or dummy variables, or it's also known as one-hot processing. So that's where we take our raw data and we kind of expand it out into numeric data. And we'll see how that looks here in a second. So let's take a look at our raw data real quick. We have a column here called work class, and it has 8 unique values, and they're all strings. So how do we turn this into a number? What indicator values does is it creates a column for every unique value. So our work class is now 8 columns. First column is just the first value, and it goes down the line. So we can see this first record here was age 39, and their work class was actually state-gov. And we know that because that's the work class column that has a 1 in it. So what this has done is it's taken our string data and turned it into numbers, which makes a lot of the math much easier. Azure Machine Learning is nice enough to not make us do this most of the time, but there are cases in which this is necessary, and we're in one of those. Now that we have indicator values, we want to be able to tell which variables are important. We're not quite to the feature engineering phase yet. We'll do that in a minute. Right now, we're doing what's called feature selection. And feature selection is using the data we have, how do we know which variables are important? We have all these raw variables. Maybe we've even created a few. Which of these are actually useful? A traditional data scientist would do this using what's called correlations, meaning they would say, okay, I want my age column, and I want to compare it directly to income. Ignore all the other columns, just age versus income. And then I do it with the next column and the next column. You do every column individually versus income. That can be misleading. For instance, you might have 2 columns that both correlate strongly with income, but if they have the same information, then together they're not very useful. Or you can have 2 columns that actually tell different stories. in which case, whenever you include both of them in your model, both of them look good in a vacuum, but when you include them together, they actually perform worse. That's called obfuscation, and it happens from time to time. So permutation and feature importance is a little bit more advanced. What it does is it takes an existing model. Good thing we have a model that came out of our twin model hyperparameters, right? It takes an existing model, and it looks at each of the variables, not in a vacuum, but looks at each of the variables with the context of the other variables already in the model. So it says, given all of the other information in the model, is this variable still important? And it does that via a pretty clever approach of it jumbles up all the values in the data set. So we have our trained model here that was trained on the actual data. And the permutation feature importance will say, okay, I want to know how important age is. In order to do that, it'll say, I want to take person 1's age and give it to person 8. I'm going to take person 8's age and give it to person 15. I'm going to take person 15's age and give it to person 3. And it just jumbles up the age column by itself, just the age column, recreates the model, and then compares the two. And it says, did jumbling up this variable affect the model? If the variable had a huge impact on the model, then jumbling up the values is going to have a significant impact. If the variable wasn't important, then jumbling up the values isn't going to matter very much. So that's what permutation feature importance does. And we can take a look at it here. Basically, it went column by column and can tell us what are the most important variables here at the top. For instance, capital gain is the most important. Obviously, capital gain being a financial metric is going to weigh pretty heavily towards income. Also, being married, your education level has impact, your age has impact, your capital loss, which is another financial metric, has impact. So we can see all of the different impacts that come from these different columns. We can also see these columns here that don't have any impact. Towards the end, we can also see any columns that have a negative impact. Before, we talked about obfuscation. Obfuscation is when a variable has so much noise or tells such a different story than all the other variables in the data set that including it actually makes your model worse. It's rare, but it happens. And here are two cases in which that's happened. One thing I will note is these zeros we see here are not actually zeros. Azure Machine Learning doesn't like very small decimals. So if we were to remove all of these columns with zeros, we would find that our model does lose some power. So I usually emphasize being careful or removing 1 or 2 variables at a time, not removing all 30 of them, and then seeing what result it has after that. But as you can see, we gained a lot of advantage from having an initial model built before we did feature selection, as opposed to a traditional data scientist who would do that before they even built their first model. So now that we've talked about feature selection, and we talked about what feature engineering is, let's talk about how we might do feature engineering. So back to the slides. Azure Machine Learning Studio is honestly my favorite data science tool out there. And I have some colleagues and buddies out in the community who agree with that. And we all generally agree that a data scientist skilled in Azure Machine Learning Studio could solve 80% of their organization's analytic needs just using Azure Machine Learning Studio. However, that 80% is not just from Azure Machine Learning Studio. If we think of the data science space as a whole, we saw how many algorithms there were up on a few slides ago. There's hundreds, thousands, probably tens of thousands of algorithms out there. That's huge. Azure Machine Learning doesn't come anywhere near having all those algorithms. It has a lot of the major ones, and that's good. However, Azure Machine Learning Studio kind of fits in this little space in the middle. What it does by default is it's good. It'll get you part of the way there, but it's difficult to have a true professional production-worthy solution that uses nothing but the default modules. However, Azure Machine Learning Studio allows you to use SQL or Python code directly in the studio. And that's really how we gain our power. That's how we get up to that 80% mark we just talked about. So let's talk about what we can do with those tools real quick. SQL, for those of you that aren't aware, is structured query language. It's a family of languages that probably the most famous family of data manipulation languages out there. And it's really good for taking multiple data sets and putting them together in joins or unions or whatnot. And it's also good at aggregating features up. So if you want number of sales over the last 3 months and things like that, SQL's generally pretty good at doing stuff like that. A quick note, the SQL we see in Azure Machine Learning Studio is not T-SQL. T-SQL is the language behind SQL Server. Instead, it's a open source language called SQLite. It has most of the same functionality, but if you're looking for some of the more advanced T-SQL features like windowing functions and stuff like that, you won't find those in SQLite, unfortunately. So on the other side of the boat, what can we do with R and Python? A lot of the same. R and Python are also data manipulation languages. You can manipulate your data. However, they don't look at data the same way that SQL does. So instead of being really good at combining data sets together and aggregating up records, R and Python are really good at working on a single record or working on a small set of records. They're very good at doing things like that. And if you need some advanced mathematical formulas, R and Python shine there because they're both pretty math-oriented pieces of software. Something they do that SQL just doesn't is you can also do model building in those. So I had one of the experiments I worked on recently that we talked about earlier. We found that in our initial data modeling phase, like we've been seeing now, our model that came out was really, really bad. Just so bad that there was no way we were ever going to fix it with data cleansing or feature engineering. So we actually revamped our problem into what's called survival analysis. And we wanted to use a model called the Cox proportional hazards model. It doesn't exist in Azure Machine Learning Studio, but it does exist in R and Python. So our Azure Machine Learning Studio allows us to import R and Python packages directly into the studio so that if we want to build a model that isn't supported in Azure Machine Learning Studio, we can build them in using R or Python. There's also ways to use your favorite R and Python IDEs like Atom or like RStudio or whatever, and then publish to Azure Machine Learning Studio. We won't talk about that here, but there are ways to do that as well. So once we think about all of those different things we can do, that's how we get to the 80%. And let's see how we would use those to really flesh out our experiment so far. Because we've done a little bit now, but we don't have a production-ready model yet. Of step 3, we go into step 4. Let's talk about feature engineering. It's difficult to do good feature engineering using base Azure Machine Learning Studio. It doesn't have a lot of tools for it. However, we have a nice tool here called execute rscript that allows us to run an rscript. This is one of the scripts that I'll have available on my blog for you guys to download. I wrote this custom for this example, so it's not super extensible, but it does work. Basically, what this does is it loops through all of the variables and creates what are called interactions. So let's look at our original data set again. Not our original data set, but the indicator variables version of it. We have a column here called work class federal gov. That is 1 if the user has a work class of federal gov and 0 if they don't. We also have another value over here. Let's say education, associates, or vocational. Let's say we wanted to combine those. Instead of looking at them individually, what if we wanted a single variable that tells us, does the user have a work class of federal-gov and have an education level of associate's degree or vocation? In order to do that, since these are 1s and 0s, we multiply. And that's how people commonly do interactions. You take all your different variables and then you multiply them together pairwise to create these 2 variable interactions. So let's go back and look at this again. So all this does is it loops through that, and it does a little bit more because we don't want to have the interaction between different types of educations or different types of work classes, because obviously nobody's going to have a work class of federal gov and a work class of student. You can't have both. You have to be one or the other. So those would be useless. So we threw away some of them. This is still kind of green. It's not perfect. I just wrote it for this experiment. And in production, we do something a bit more advanced. But as you can see, if we go down to the results of here, We have gone from 105 columns, I think is what came out of the other one, to over 9,000 here. So using just what was 30 lines of code in R, we were able to create thousands of features. That's the advantage of feature engineering. We can create massively, we can create very large scale data sets using R or Python or SQL to really get the most out of our data. So what impact did those features have on our model? Let's take a look. Our old model had an accuracy of about 86.3%. This model has the same exact accuracy. Those features didn't help. And that's fine. It didn't take us very long to put it together. So it's not a big deal. But the advantage this had was we knew our good accuracy going in. We know that those features aren't important because we had an initial model to base on. That was the advantage of postponing the feature engineering like we talked about. Since we waited until we already had an initial set of models to build it, now we know where we've come from and how far we've gone, which is very important because this is an experiment after all. We want to know change. So how do we put this all together? We've talked about a number of things. We've talked about using twin model hyperparameters to choose a model. We've talked about saving your feature selection for later. We've talked about saving your feature engineering for later. How to use R to do that feature engineering. So let's put it all together. This is an approach that my boss likes to call the kitchen sink approach. So if we scroll up, basically I have this experiment here that I just bring to virtually every customer we have. Once we have a data set and we want to see, okay, what would an initial model look like? We take our data set with our new features and everything, and we split it the same way we always did. We run it through every single two-class classification algorithm in Azure Machine Learning. There are actually 14 different combinations that you can use with twin model hyperparameters. We take all 14 of them, run all 14 of them against the twin model hyperparameters down here, and these all get their own results. We use some SQL code, and I'll send you guys this code as well, to combine all of them together. So we combine all 14 of these together. One disadvantage of the SQL transformation in Azure Machine Learning Studio is it only supports 3 inputs. So in order to combine all 14 into a single, it takes me, 8 different transformations to combine them all into one. That's unfortunate, but it is what it is. And once we combine that, we can just put it all together and order it, and we can see our results. We can see that we've tested 280 different models here. And we can see that the two-class boosted decision tree with 33 leaves and 9 leaf instances and a learning rate of 0.04 and all that has an accuracy of 86.1%. That's the best model we could have ever gotten out of this data using Azure Machine Learning. And in practice, it usually takes us 10 or 15 minutes to put this together. To put this experiment together, we click run, we go to the water park with our families, come back the next day, and we have an initial set of models built already that gives us a starting point. So instead of wasting countless hours, days, weeks, months doing all of this stuff that may not even be useful, we get a good baseline, and that really educates us all along the way, and it allows us to be true professionals. Instead of walking in and saying, I know the answer because I've done this for 20 years, we get to walk in and say, I know the answer because your data told me. So those are the 4 tips from the pros, and that's how we start engagements, and that's how we really get that 80% value out of Azure Machine Learning Studio. So we have 15 minutes left, and I do want to leave time for questions. For those of you that, if you have a hard time following this because it was a little bit too much Azure Machine Learning Studio for you, there was a more baseline presentation gave about a month ago. It is on the Past Cloud Virtual Chapter YouTube channel. It's called Making Data Science Easier. So if you wanted a introduction to Azure Machine Learning Studio, where it fits in the space and why you would ever use it, that's a really good presentation to get started. I know there are more machine learning presentations coming up. There's the one on Saturday he talked about. I know Ginger Grant's giving a good one here in a week or two. In a couple of months, I'm giving another one that is not Azure Machine Learning related. It's called What is a Data Scientist and How Do I Become One? And it talks about my experiences as becoming a data scientist and what different types of data scientists I meet are and how you could become one if you wanted to. So there's my contact information. I want to thank everyone for coming, and I'll open it up for questions.
All right, thanks, Brad. At this point, we actually don't have any questions, so we can leave it open here for a couple seconds, 30 seconds or so, to see if any come in, but if not, we can wrap it up for today. And I do really thank you for presenting for us this week. Just like the last one, a great presentation today.
Thank you. I mean, it was great to be here.
All right. So we did get one question that came in. Any books that you recommend for getting into data science and Azure Machine Learning?
Oh, that's a great question. I don't know the name of the book off the top of my head. I read one that does a complete introduction to Azure Machine Learning. If the questioner would send me an email, I will dig up that book. I've actually got the ebook version of it, so I'll send it to him for free.
All right. I will get that email over to you. And then
Okay.
The next question that came in is a Ph.D., et cetera, mandatory to be a data scientist?
Oh, that's a great question. That's a lot of what that other presentation touches on. But I hope that throughout this presentation, I have shown that you don't need a PhD to do this. As you saw, nothing we did today really required advanced knowledge about the different models. I'm not a traditional data scientist by any means. I don't have a PhD. My math skills are good, but by no means spectacular. So what I find much more important is strong data skills. So getting the data together and then allowing Azure Machine Learning to do a lot of the work for you can really bridge that gap. And on another note, I find it very helpful for aspiring data scientists that say, I don't know enough about data science right now. Azure Machine Learning is a great way to learn data science because it'll allow you to produce results without knowing yet all the inner workings of all the algorithms work.
All right. Well, that is all the questions that we had for today. So to follow up, I will get you that email address from the one questioner, and we will wrap things up for today. Thank you again, Brad.
Okay, thank you.